Okay, hello and welcome back. In this video, we're covering section 12.3. So we'll look at another kind of sequence called a geometric sequence and geometric series, meaning the sum of the first n terms of a geometric sequence. And then we'll also look at infinite sums and whether they converge to a single value or they diverge, meaning they just get infinitely large in the positive or negative direction. So first let's define what a geometric sequence is. So an arithmetic sequence was one where we just add the same value to the previous term in order to get the next term, the difference between two consecutive terms with some constant value. Well, a geometric sequence is slightly similar, except we would be multiplying every time to get to the next term. So an example of a geometric sequence would be 2, 6, 18, 54, 162. If you divided consecutive terms, you would see that each time 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54, 54 times 3 is 162. So each successive term is multiplied by the same value r. So in this case, we would say r equals 3. And this is what we'll call the common ratio. And so we can define this recursively. We could say the nth term of a geometric sequence should just be the previous term times r. So we can write that as r times a sub n minus 1. So that gives us our recursive formula. So from the text, geometric sequence is defined recursively in the way we just did. So we have our first term, and then our common ratio is r. So we'll list our first term, and then the nth term is the previous term times r, where r is the common ratio. So let's look at how we can determine first if a sequence is geometric. We're saying that if we divide consecutive terms, we get the same value every time. So we can do this generally. So in example 2, we have s sub n defined as 2 to the power of negative n. So let's find the first term in the common ratio. So s sub 1, our first term, just plug in 1. So 2 to the minus 1 power will give us 1/2. That will be our first term. So our common ratio we should get by taking a general term, s sub n, and divide that by the previous term, s sub n minus 1. So if we do that, s sub n is 2 to the minus n. S sub n minus 1 would be 2 to the minus n minus 1 in parentheses. So we have a division of two exponential expressions where the base is the same, so we can re-express this as 2 to the power of minus n minus n minus 1. Kind of tricky with all these negatives, but really we're just doing like x cubed over x squared. You would subtract the exponents. So we're just subtracting these two exponents. So let's clean this up. This would be 2 to the power of minus n. Let's distribute that negative inside first, so minus n plus 1. So that looks like 2 to the power minus n plus n minus 1, or 2 to the minus 1. So we get 1/2 again. That will be our common ratio. But if we divide two consecutive terms in the general form and we get some common constant, it means every time You go to the next term, you're multiplying by the same value. And that's what makes it a geometric sequence. So let's look at another example. Here we're given t sub n is 3 times 4 to the power n. So let's find the first term in the common ratio. Our first term would be t sub 1, so 3 times 4 to the first power, which will give us 12. And our common ratio we'll find by doing t sub n over t sub n minus 1. So that would be 3 times 4 to the power n over 3 times 4 to the power n minus 1. Well, our 3's will cancel. And we're saying we're dividing 4 to the power n by 4 to the power of 1 less than that power. We should just get 4 left over, but we can still use our rules of exponents. This would be 4 to the power n minus n minus 1. That would be 4 to the power n minus n plus 1, or just 4 to the first power. So our common ratio will be 4, meaning we'll start at 12, and then with each successive term, we'll multiply by 4. So let's build a general formula for the nth term that's not recursive. So let's start with our first term. A sub 1 would just be a, or a sub 1. Then our next term we'll get by taking our previous term and multiplying by r. Then, oh, this would be a sub 2. So our third term, we would take our previous term, which is a sub 1 times r, multiplied by another r. So we can write that as a sub 1 times r squared. Then our fourth term, we'd multiply by another r, so let's just write that as a sub 1 times r cubed. So we can imagine this pattern continuing. Notice this is n minus 1. So we can say in general, a sub n should be our first term times r to the n minus 1 power. This will be our nth term of a geometric sequence. So let's use this in order to find a particular term in a geometric sequence. In example 4, they want us to find the nth term of this sequence, which is 10, 9, 81 over 10, 729 over 100, and this continues. It's kind of tricky to see the pattern. We're told that this is a geometric sequence in the prompt of the question, so that's useful. That means we know for sure there should be some common ratio between every successive term. So in order to find that, we can just pick two terms and divide them. So let's take this term 9 and divide by 10. That will give us our common ratio. So our first term is 10. Our common ratio would be 9 over 10. So that means our nth term, a sub n, should be our first term, which is 10, times our common ratio, 9 over 10, to the power of n minus 1. And we can always check to see if this produces our sequence. If we plug in a value of 1 for a sub 1, notice we would get a 0 exponent, so that will just give us 10. If we plug in 2, that would be to the power of 1, because 2 minus 1 is 1. So it would be 10 times 9 over 10. The 10s would cancel, and we would get our 9 value. And then from there, we can see each time we're multiplying by another 9 over 10. That'll give us 81, gives us a 10 in the denominator. So B asks us to find the 9th term of this sequence. Let's just find a sub 9. That should be 10 times 9 over 10 to the power of 9 minus 1, so to the 8th power. So multiply that out and you get 4.3046721. Part C asks us to find a recursive formula for this sequence. So for a geometric sequence, a recursive formula, you list out the first term, which is 10, and then our nth term would be the previous term, a sub n minus 1, times our common ratio of 9 over 10. So that's the nth term formula, but we can also find sums of geometric sequences. So let's jump over here. Scoot this up. So let's just work with the formula. I would challenge you again to try to build this on your own. But we're told the sum of the first n terms of a geometric sequence. So we can actually write that out in summation notation or using this s sub n notation. But notice we're adding up all of the first n terms of a geometric sequence. So let's write it out in summation notation. This would be the sum k going from 1 to n, so the first n terms, of a sub 1 times r to the power k minus 1. That's our geometric sequence. This all will sum up to a sub 1 times a fraction 1 minus r to the power n over 1 minus r. So if we know what our common ratio is in our first term, we can find out what it should sum up to using this formula. So in example 5, let's find just the common expression, the general expression, for the sum of the first n terms. So I'll leave this here. So we're looking at the sum k going from 1 to n of just 1/2 to the power k. So they have this expanded out. I'll write it out too. That means we would be doing 1 over 2 plus 1/2 squared, so 1/4, times another 1/2, so plus 1/8. And this continues until we get 1 over 2 to the n power. So we need to find, based on our formula, our first term and our common ratio. So our first term, a sub 1, we can see that from the expansion. That's just 1/2, or we can plug in 1 for our k value here. Our common ratio is 1/2 each time it's being multiplied by 1/2. So r is also 1 over 2. So let's plug into our formula. This sum should be equal to our first term, which is 1/2, times the fraction 1 minus r to the n. Our r is 1/2, so b to the nth power, over 1 minus r, so 1 minus 1/2. We can simplify this a bit. The 1 minus 1/2 in that denominator will give us just 1/2 again. 1 minus 1/2 is 1/2. So this 1/2 multiplied on the outside will cancel with that 1/2 in the denominator. So this simplifies to 1 minus 1/2 raised to the power n. This is equal to the sum of the first n terms of 1/2 to the power k. And so if we were asked to find the sum of the first 1,000 terms of this sequence, we would just need to plug in 1,000 to this n term. It's a good This is a good opportunity to think, well, what would happen if n gets extremely large, as n gets to higher and higher values, maybe like 10,000 or a million? What will happen to this sum? So we will see that it will have two different kinds of behaviors. Either it will converge to a single value, which seems a little bit counterintuitive, but there's some sums that we can add that have an infinite number of terms that will never surpass a particular value. It has some kind of upper bound or some kind of limit. Or they'll just keep getting larger and larger. In that case, we'll say that they diverge. So let's define what these two terms mean. So we're looking at an infinite geometric series. This is when we'll never stop adding terms. So we can write that as a summation. We'll still start at 1, but we'll say the upper bound is infinity, meaning it will never end. And we'll have some geometric sequence inside. So we have some conditions on whether it will converge to a single value or if it will diverge and just continue to grow. And the condition is based around this R value. Let's actually look at this previous example. Imagine this n value is getting larger. It means we're raising 1/2 to higher and higher powers. We already saw that the values get smaller when to the first power it's 1/2, second power 1/4, 1/8. These are smaller and smaller fractions. So eventually we can say that this second term will, in a sense, it will like evaporate. It will go to 0 as n gets larger and larger. So even though our sum will be infinite, if we were to say do this sum as n goes to infinity, even though we'll never technically stop adding terms, eventually we'll just be adding essentially zeros. So we'll have the sum of our first bunch of terms and then plus some infinitesimally small values, which eventually will be like adding 0. So the sum will eventually stop at some point. It will converge to a certain value. So the condition here is that this R value is some fraction. And they state it in this way. They say if the absolute value of R is less than 1. Another way to say that is that R is greater than -1 and less than +1. Because it could be negative as well. But as long as it's some fraction, that means every time we raise it to a higher power, it's going to get smaller. If that's the case, then we'll say that the infinite series converges. And then we have a formula for its convergence. So we're told that if, we can go off this previous statement, if the absolute value of R is less than 1, meaning that it's a fraction, then the sum converges, or it's going to be equal to our first term divided by 1 minus R. So that's our formula we can use. Otherwise, and they don't have it stated here, and I'll just add it in. Meaning that R, let's say the absolute value of R is greater than or equal to 1. The series diverges. So let's look at example 7. We want to determine whether the geometric series converges or diverges, and if it does converge, let's find its sum using this formula. So we're given the infinite sum, k going from 1 to infinity, of 2 times 2 over 3 to the power k minus 1. So this is a geometric series with an R value of 2/3. So that's a fraction. It's less than 1, greater than 0. So that means it should converge. And we can see in the expansion, notice it's getting smaller. Numbers are approaching some value. So our first term is going to be positive 2. Our R value is 2/3. So this should converge based off of our formula. It would be a sub 1 over 1 minus r. So our first term is 2 over 1 minus the r value of 2/3. So that's 2 over 3/3 minus 2/3, so 2 over 1 over 3. So divide these two and you get a positive 6. That means this infinite sum will add up to a whole value of positive 6. So if the r value is some fraction less than 1, then the infinite geometric series will converge to this value, your first value divided by 1 minus r. Otherwise, if r is greater than 1 or even equal to 1, then it will diverge. It'll just keep getting larger. Our last example, example 8, is an interesting result. They're saying to show that the repeating decimal 0.999 repeating is equal to 1. It seems counterintuitive. So we're looking at 0.9999, and that continues, meaning we can put like a repeating symbol here. Well, we could express this as an infinite sum. We can say this is 9/10. That would give us our first place, plus 9/100. It gives us our second place, plus 9/1000. And this would continue indefinitely. So let's try to express this as a summation. This would be the sum k going from 1 to infinity. Now let's make our general term our a sub n for this. Our first term, so we're following a sub n, should be our first term times r to the power n minus 1. Our first term is 9 over 10. The common ratio, each time we're multiplying by another 1 over 10. So this is 9 over 10 times 1 over 10, and we'll say to the power k minus 1 inside the summation. Well, we have an r value of 1/10, so it is a fraction, which means this series should converge to a specific value. So it will be our first term, a sub 1, which is 9 over 10 over 1 minus our common ratio. Well, 1 minus 1/10 is 9 over 10. So 9 over 10 over 9 over 10 is equal to positive 1. So we're saying that 0.9 repeating, which can be expressed as this infinite sum, converges to this value of positive 1. So a pretty interesting result. All right, that will be, oops, jumped to the wrong screen. That'll be it for this video. So we covered determining whether a sequence is geometric. We found the formula for a geometric sequence, so that was a sub n equal to our first term times the common ratio to the power n minus 1. We found the sum of a geometric sequence if it's finite. So if we say s sub n, or we can describe that as a sum k going from 1 to n of our geometric sequence. If it was finite, then it's just our first term times 1 minus r to the nth power over 1 minus r. And then we brought up this idea of convergence and divergence, which involves an infinite sum. So for sum is infinite, k going from 1 to infinity, and if, specifically if r is a fraction, so we can say the absolute value of r is less than 1, then it converges to a sub 1 over 1 minus r. And we can kind of see that here. If we let n get infinitely large, and we're saying that r is some fraction, that term eventually goes to 0. It kind of evaporates. So more on that theme later on in calculus when we introduce the idea of limits. But for now, we'll just have to use a bit of intuition to see that that term will go to 0. And we didn't cover it here, but in the text there's some applications to annuity problems. So if you're into the financial side of mathematics, it's a cool application of some of these concepts. So that'll be it for this video, and I'll see you next time.